Section 11.2 is what we call a Goodness of Fit test. In the previous sections, we've looked at testing a claim about one or two means and one or two proportions. What we're going to look at now is looking at one sample of data. We're going to look at several proportions and test some claim about those proportions. So let's start off with an example. A survey of 40 randomly selected men and 40 women collected weights. By analyzing the last digit of those weights, researchers can verify that the weights were obtained through actual measurements instead of just having the subjects report their weights. Given the following frequency distribution of last digits, test the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. This would suggest that people report their weights. So looking at this data, we've got one sample of 80 people, and we want to look at the proportion of zeros that were the last digit of weights that were given. So for example, this would include people whose weights came in at 130, 140, 150. The last digit of 1, of course, would come from people who had last weights of, say, 121, 161, 181, 251, etc. So out of those 80 people, 7 of them had a last digit of 0, 14 had a last digit of 1, etc. So what we're looking at is if these were measured accurately, then we would expect the frequency of each of these last digits to come up roughly about the same. Whereas if they were reported, we would expect that maybe that frequency would be changed somehow. You might get a lot more zeros or a lot more 5s, or you might just get a lot more of some other number. So step 1, just as before in previous sections, we're going to identify the claim. So the original claim is that the digits do not occur with the same frequency. So that is at least one of the probabilities, p sub 0, p sub 1 through p sub 9. These, of course, are our p sub 0. This is our proportion of zeros. This would represent our proportion of ones. And of course, when I say proportion, I mean 7 out of all 80, or 14 out of all 80 would represent our proportions. So we label this as P0, P1, P2, P3, all the way down to P9. So we're claiming that at least one of those, P sub 0 through P sub 9, is different from the others. So the opposite of the claim then is that each of those probabilities or proportions are equal. They all equal the same thing. So just as before, our null hypothesis will be the one that includes all the equality. So in this case, we're saying all the probabilities or proportions are the same. Our alternative hypothesis in this case then will be that at least one of those is not the same as the others. So just as before, if we are not given a significance level, we'll use 0.05. And then step 5, finally, we'll identify the test statistic. We're going to use what we call a chi-square test statistic when we're testing multiple proportions like this from the same sample. So the test statistic looks like this. The calculations are a little bit complicated, so we're going to use tables to keep track of our intermediate calculations and then finally get down to the actual test statistic that we want. You may find Excel helpful here. So just to clarify what the symbols mean, O is going to be our observed frequencies, and that's what we get from our data. So this is our O column, our observed frequencies. E then is our expected frequencies. And we'll talk about how to calculate or come up with the expected frequencies next. So the expected frequencies, since we decided that, or since our null hypothesis was that each of the proportions was the same, or should be the same, we would expect it to be the same, and since there were 80 observations, we would expect 1/10 of these 80 observations to have the last digit 0. We would expect 1/10 to have the last digit 1. if you're confused about where I'm getting 1/10, it's from the fact that there are 10 different categories here, and we're saying we would expect them all to be the same. So our expected frequency then is calculated by taking the number of observations that we have, in this case 80, multiplying by the probability that we would expect that to come up, that category to come up. So in this case, I have 80 observations, and for each observation, or each last digit, I would expect 1/10 of them to be 0. So that means my expected frequency of zeros is 8 out of the 80 that we're looking at. The same would go for the expected number of ones to come up. We'd have n times p, or 80 times 1/10. And again, for 2, and again, for 3, 4, 5, 6, 7, 8, and 9. So in other words, we would expect 8 of each last digit out of 80 total. So now part of our calculation for our test statistic is taking our observed frequencies and minusing or subtracting the expected frequencies. So in this case, for the zeros, I have an O minus E of -1. For 1 last digit, I have an O minus E of 6. Moving on down, just subtracting each column. The next thing to do then is square each of these numbers. So if I square -1, I get 1. I square 6, I get 36. On and on down, all the way down to last digit of 9. Then the next to last thing we do is take each of these numbers in our O minus E squared column and divide those by the E that we had come up with earlier. So this is our O minus E squared divided by E column. The last thing to do then is add up each number in this O minus E squared over E column, and we finally get our test statistic of 11.25. So we found our test statistic to be 11.25. Is calculate the critical value. So we'll use the chi-square distribution table, which you can find on Canvas where you found this lesson, or if you like using Excel, you can use the formula CHIDIST and put in the required information into that formula. So before we talk about the chi-square distribution table, we need to know what the degrees of freedom are for a test statistic like this. What we'll use is the number of categories minus 1. So in this case, since we have 10 categories, subtract 1 from that, we'll use a degrees of freedom 9. So you should download the chi-square distribution table and get something that looks like this. We're going to use 9 degrees of freedom in this case, so we'll be in the 9th row here, and we're going to be in the 0.05 column. And just a word about this notation, the 0.05 indicates 0.05 area to the right. So our critical value then is 16.919. So we found our critical value to be 16.919 and our test statistic to be 11.25. So the question is, do we reject or fail to reject the null hypothesis? Well, one thing you must know is that with a chi-square distribution test, every time it's a right tail test. So the nice thing about these are we don't have to worry about left tail, right tail, or two tail tests. These are all going to be right tail tests. So if your test statistic is to the right of your critical value, or in other words, if your test statistic is greater than your critical value, then we'll reject the null hypothesis. So in this case, since our test statistic was not greater than our critical value, we fail to reject the null hypothesis. So now the question is, do we support the claim or do we not support the claim? So the null hypothesis was that each digit occurred with the same frequency. The claim was that at least one of those frequencies was different, suggesting that these were reported weights instead of measured. But since we failed to reject the null hypothesis, we cannot support the claim because we cannot reject the idea that each digit occurred with the same frequency. So let's look at another similar but different type of problem. In this case, what we're going to see is that the expected frequencies are going to be different than one another. In other words, they won't all be the same like they were in the previous problem. So in baseball, the World Series is a best-of-7 competition, which means there can be 4, 5, 6, or 7 games played. The table below includes the number of games played in the past 99 World Series. Also included in the table are the expected proportions of each number of games. Test the claim that the actual number of games played fits the distribution given by the probabilities. So we're given some probabilities, and the claim is that these are the expected proportions, essentially, of the number of World Series games it plays to each number of games. So, in other words, the expected probability of, or the expected proportion of games that play World Series that play to 4 games is 2/16 or 1/8. The expected proportion of World Series that plays to 5 games is 4/16, etc. So we'll identify the claim as the proportion of World Series that go to 4 games is 2/16. The proportion of World Series that goes to 5 games is 4/16, etc., etc. So these were the proportions that were given to us, and our claim is that those proportions equal what was given to us. Then the opposite then is at least one of those proportions is not equal to the claimed value. So the null hypothesis, again, will come from the one that has all equality in it. And then the alternative hypothesis will be the one that does not have equality. And just as before, we'll use a 0.05 significance level. So a similar table to what we did last time, the main difference here is that for our expected frequencies, we won't get the same number in each row. So the p's in this case, when we do our calculations, are going to be those p's that were given to us for each number of games. The n, of course, is the number of games we looked at. So you can either add up this column or realize that the original problem said 99 World Series. So the n will be 99. The p is the probability or proportion that was given to us. So multiply those together, and here we're saying the expected frequency out of those 99 games, we would have expected 12.37 games to go to 4 games. Then we would expect 24.75 of the World Series to go to 5 games, 30 out of those 99, or 31 almost out of those 99 World Series to go to 6 games, and about the same number going to 7 games. But now the rest of this column is the same as what we did before. We'll take our O column minus our E column, and put that in our next column here. So we get 6.625 is the difference between the O and the E for 4 games, etc., etc. The next thing we do is square each of these O minus E. And finally, take each of these O minus E values and divide them by the E value that we came up with earlier. So in other words, for this first row, I'll take 43.8906 and divide it by 12.3750. Do that for each row, and the last thing we have to do is add up each of these numbers in the O minus E squared divided by E column, or the last column, to get our test statistic. And here we get a test statistic of 7.885. So now let's calculate the critical value, and we'll look at the chi-squared distribution table here. Now there were 4 different categories in this case, so that means that is the 4-game, 5-game, 6-game, and 7-game categories. So those are our 4 categories, which means we're going to use a degrees of freedom 3. Again, we're using a 0.05 significance level, so our critical value is 7.815. So So we found our critical value to be 7.815. Because our test statistic was greater than the critical value, we reject the null hypothesis. So we're rejecting the null hypothesis, which said the expected proportion was of 4 games. So in other words, the expected proportion of World Series that goes to 4 games was 2/16, etc. We're rejecting that idea, which means it suggests that at least one of these proportions is not the same. So since our null hypothesis and our claim were the same, and we rejected the null hypothesis, we cannot support the claim. So again, that means we're suggesting the idea that at least one of these proportions is not equal to the claimed proportion.